So our next speaker is Francisco Navarro from Flatiron Institute, and he's going to talk about cosmic graphs. And he did his PhD in astrophysics in Valencia, Spain, and he did lots of postdocs in Italy, New York, and he's a research scientist currently at Flatiron Institute. Thanks.
So thank you very much. Can you hear me? Can you hear me well? Maybe some, maybe not. Hello, hello, no. I can speak up, but very I can speak up. So first of all, thank you very much for the invitation. It's a pleasure for me to come here. So I'm coming from, I would say, maybe slightly different words. I'm gonna mostly talk about, applications, about how we can use like graph neural networks to do, like, in my opinion, like really cool stuff, mostly in astrophysics. So I can change the slide. Okay, better. So this is the outline of my talk. I was assuming that maybe not everybody here is familiar with cosmology. So I'm gonna give you like a very kind of high-level introduction about what cosmology is and what are the problems that we are facing. And then I'm gonna talk, from a historic perspective, what is the way in which we have been tackling these problems, very standard pen and papers, basically very numerical, let's say, heavy calculation distance. And then I'm going to tell you about what are the things that we can do these days with TMS, and it's really kind of a revolution, I would say, and how we can really move on from this. So what is cosmology? So this is what the cosmology is according to ChatGPT. So you can see that this is what the things that cosmology is. I'm not very super nice, but I like this kind of image because it really shows a little bit what we really do in cosmology. So imagine that you were able to put the entire universe inside a crystal ball. So basically in cosmology, we will basically study what are the properties inside the crystal ball. So things that we care is like, what is the origin of the universe? What is going to be its fate? What is the composition of the universe? What are the laws of the universe? And what is the structure? What is the dynamics? And all this kind of things. So basically, properties of the universe as a whole. So I don't know how much you know of this, but this is basically the composition of the universe as we understand. We believe that 5%. Yes. So we believe that only 5% the variables are only 5% of the energy contained in the universe. And variables is basically everything that we know. So all kind of atoms, molecules, everything that we know nature is basically what we call variables. And what is really surprising is that in the entire universe, only 5% of it is made up of this. So we are kind of a weird thing for the universe. So we believe that the dark matter represents around 25% of energy contained in the universe. So we don't know what dark matter is. It should be some kind of fundamental particle, but we don't know much. It should be something there. But we have a lot of evidence that is there, Basically, we look, for instance, at how fast the galaxies are rotating, and they are rotating much faster than what we can really explain from basically the light and the data and the stars and everything that we see. On top of this, what we are finding is that the universe today is expanding. And this maybe makes sense because we believe that the universe started with some kind of explosion, the Big Bang. So you will expect that the universe will expand. But what we didn't know, and it was really, really surprising, is that the universe today is accelerating its expansion. So there is really no way for us to understand how that is possible. And basically, all our ignorance of this, we claim that this is due to dark energy. So we don't know what this thing is. It probably is some property of the vacuum, there is nothing else. But what you can see is that most of the energy contained in the universe is basically in this dark energy. So, cosmology is a kind of weird science where most of the things on it is something that we don't know. And the thing that we know is only something like, let's say, the big. So cosmology, as in many other branches in physics, and like in many other disciplines, would have, in our case, this is the standard modeling cosmology. And this model is remarkable, basically because we're able to then obtain very large variety of cosmological observations. For instance, this is for galaxies, basically in the local universe. And this is a picture of the baby universe. This is a picture of the entire universe, 13 billion years ago. It's remarkable that we can do these things. So we have a model, and I will explain that cosmologists have done the most massive data compression that you will ever do. Basically, because we have a model that basically has two parameters, 5 and 10, we are able to explain the entire universe. The entire universe. This is the largest data compression I will argue ever. So I'm not going to go into the details, it's not important, but some of these parameters really describe properties of the universe as a whole. For instance, this one is the fraction of the energy contained in the universe that is made up of atoms that we were talking before. And there are other parameters that describe the properties of that matter, the properties of that energy, and all these kind of things. So what is the goal of cosmology? So in cosmology, the most important thing, one of the most important goals for us, is to explain the values of these guys with the highest numbers. That's kind of, I would say, the most important goal. So why do we want to do this? Because we want to know about fundamental physics. We want to know what dark matter is. We want to know what dark energy is. We want to know about the universe. So by measuring these parameters with the highest accuracy, we will be able to rule out different hypotheses about what dark energy is or what dark matter is. So to a very high level, this is basically about cosmology. We have a model that is remarkable. We have some parameters, and we just want to measure these parameters with the highest. So how do we do this in practice? So basically, this is basically a parameter influence problem. So what we do is we carry out observations, and you can think of this like we measure the position of galaxies in the sky. And until now, I would say we never knew how to work with this problem. If someone gives you like a galaxy catalog where there is a position here, a position there, we didn't know how to work with this problem. It's a very high-dimensional problem. We don't know how. So in cosmology, typically what we do is to compress the data into a low-dimensional representation. And it can be anything. It can be the number of galaxies, the number of pixels where there is no light. And then from the theory side, we make theoretical predictions. So for instance, these data represent the value of cosmological parameters. And basically what we want to do is that given a different universe, let's say with a different composition, with a different mix of matter, dark energy, how will this, let's say, summary statistics, cosmology will call this summary statistics, how will this look like? And this is a little bit the problem of cosmology is that fortunately we have one single universe. So we really need theoretical predictions. We cannot just take a look at the universe and know the composition. So we need really theoretical predictions. So, historically, the question has been like, what is the best way to compress it, right? So, we know that under certain conditions, the universe resembles what we call like a 1000 density. But it's basically a very particular, let's say, structure of the perturbations. And we know that there is at least some statistics, the power spectrum. So in case that you don't know statistics, imagine that you have an image, you go to Fourier space, and basically you make a histogram of the amplitudes of the models. That's very much what this is. So under certain conditions, we know that this is really ideal. Summary statistics. And this is really remarkable because, again, this is like a picture of the universe 13 million years ago. In this case, we are able to start every single bit information. We are able to determine these cosmological parameters as good as you can learn. That's my opinion of the mathematics. The problem is called multivariation. Like distribution of galaxies, let's say in the local universe. We don't know how to characterize these things. We don't know what is the, let's say, the data compression that fully characterizes the statistical properties of this. And this is a problem that can be formulated in very rigorous mathematical terms. You can ask mathematicians and will tell you that this is basically mathematically untrackable. So let me very briefly talk about the historical perspective here. I would say even until maybe 5 years ago, most of the community have been doing kind of pen and paper calculations using this power spectrum. And basically what we do is some kind of Taylor expansion. You have some equations. You assume that there are perturbations that is, say, small. And basically you do a Taylor expansion. If you know that at some point it's going to converge. The problem of using this kind of things is that if the perturbation is large enough, you need like basically the infinite number of points. This will not work. So recently, the community has been shifting a little bit more into going to numerical simulations. And the good thing about numerical simulations is that you can just solve your equation numerically. And this is invest for value. I want to show you a few models. I spent too much time in these models, so you need to see that. So what you can see here is the distribution of matter in the universe. This is what we call resting. So C equals 0 means today. Very high resting means very little. So this is how the universe look like. Let's say very early on. We believe the universe was very homogeneous, very isotropic. So that's why you see everything looks very similar. And basically what happened is that in this simulation we only have gravity. And what gravity does is to amplify these perturbations. These perturbations are one at a go. For instance, they are here, I don't know how well you can see this, but soon I think you should be fine. And you can see that matter starts clustering in this object that we call dark matter. And these are basically the regions in the universe where galaxies are going to live. You have a very large concentration of dark matter there. Galaxies are going to be present. And these halos are typically connected by things that we call filaments, where the scale of dark matter is high, but not so high. And then there are regions of the universe where there is basically nothing. We call these cosmic waves. So this is another model. So what you can see here is two different universes. They have the very same initial conditions. The only difference between them is that there is more dark matter in this one than in this one. And I don't know if you can see that there is a kind of gap here in the middle. And as we move from one universe to the other one, let's take a look at this. This is a dark matter field. And when we move from one universe to the other one, things change. The position of these dark matter halos change. Their masses and all the internal structure of these things. So basically what I want to illustrate with this movie is that when you change the composition of the universe, when you change the laws of the universe, the spatial distribution of galaxies is going to change. And now we can invert this argument, say like, if we now look at the distribution of galaxies, we can see directly on the sky. Can we infer the properties of the universe? So that's basically what, let's say, more of us. Just to conclude this part, let me mention that in the very last 5 years, the community has been spending really a lot of computing time running numerical simulations. So we have very up-to-date theoretical predictions. These days, we are basically having of the order of hundreds of thousands of these kind of numerical simulations with petabytes of data. And basically, the community has reached like a generic conclusion. And the conclusion is that whenever we look at things, compress the data in ways different to the standard way that we have in the model, we gain information. Can start much more information. And the second thing that is very important is that whenever we look at the universe on smaller scales, we do better. So what is the problem of looking at the small scales? So because we are field, Because we look at the galaxies, we say that a lot of them, but we never really look at them like this. When we analyze the data, we need to blur everything. And you wonder, like, why do we do this? So let me explain. So imagine that we have a galaxy here, and this galaxy has a supermassive black hole in the center, and this supermassive black hole is basically releasing this gigantic amount of energy. So the thing is that this gigantic amount of energy that is released by a supermassive black hole is not only affecting the properties of this galaxy, but it's also going to affect the properties of all the galaxies that are near. The thing is that we don't know much about the physics of these things. This is basically our main intention right now. That as we look at the universe on a smaller and smaller scales, we need to deal with something that we really simply don't know. And I have another mode to show this. So this is one of our situations. Also, look at this. This is a galaxy, and all these dot points are galaxies. And you can see that there is a supermassive black hole, and this is like the reference of the galaxy. So you can see that the energy released by this supermassive black hole is basically heating up all the intergalactic medium, and it's basically affecting the properties not only of these particular galaxies, but also the galaxies that are near. So let me conclude just this first part. I always like to make this comparison, and it's like imagine that we were like 100 years ago, and we were looking at a hologram like this. At that time, people were able to read some fragments about this. I think they were able to find some patterns, something like that. But most of the information here was lost. Simply didn't know how to do this. I have the feeling that with Cosmology, we are in a very similar stage where we have a lot of data. It's not a problem of data. The data is beautiful. It's not a problem. It's simply that we don't know how to do this. So now let me talk about what in the very last few years the community has been doing using this kind of numerical deep learning approaches. But before this, let me talk about the data set that we're going to use, because this is like really important. So the data set that we are basically using is coming from this project that is called Cosmology and Astrophysics with machine learning simulation. This is the largest set of state-of-the-art hydrodynamical simulations ever produced, and I have more books. So this is one example of one of these hydrodynamical simulations. What you can see in blue. Sorry, I mean, it's a little bit larger, I think, from Zoom, but more or less you can see. So in blue, you can see the gas density, and in red, you can see the gas temperature. And you can see all these explosions going on. These are either supernovae that are exploding and releasing energy, or could be like these supermassive black holes that are again releasing this gigantic amount of energy. So the reason why we run these simulations is basically because these are the most accurate theoretical predictions that we have right now. And the reason for this is basically because gas formation is a complicated process. You have dark matter accumulating, forming these dark matter layers we saw before. Gas is going to fall, this gravitational potential works. It's going to cool down from small stars, it's going to fall galaxies. But these stars are going to die at some point. Some of them are going to explode as a supernovae. Some of them are going to form a supermassive black hole like this. And the supermassive black hole is going to release all this energy. Gas is also emitting gas to the filaments. And galaxies themselves are net. It's really complex. It's really complicated, this process. And that's why we rely on this kind of, let's say, I would say, very sophisticated mental simulation. So if these simulations are really expensive, being able to run 1,000 of them is very good. Another thing is another thing that is very important is like in cosmology and in astrophysics. Basically, because we don't know the physics of these supernova explosions, these energy release and supermassive black holes, there is not like a single solution. Let's say that different groups has proposed different solutions on how to model these astrophysical processes, and probably all of these things are wrong. and nothing better. Represent reality, that is the very best. So everything that I'm saying is that for us, it's super important to don't rely on a simple simulation, because that simulation is likely to be wrong. If you want to develop a model to apply to the real data, real universe, at the very least, you need to make sure that your model works in all cases. And what I'm also in this movie are basically 6 different simulations. Each of them has the same initial conditions. Each of them has the same composition of the universe. Each of them has the fiduciary model of astrophysics, of how to read and all these things. Now, what you can see is that they do very, very different. Right? There is this one that is picking up the gas very early on. There is the one that is gigantic jets coming from supermassive black holes. And then there are others that they look very different. The important thing here is that all the simulations basically reproduce the real data. So we have 6 different types of simulations that give the same answer, even though they are completely different. When you train your machine learning model, it's very important that the model works at the very least in all these different types before we ever apply this to it. But that's something that is totally very, very important. Finally, so this simulation was basically designed to train neural networks. So every simulation has a different morphology of the cosmic wave. You can see that when you change from one simulation to the other, things change. Every simulation has a different cosmology, and every simulation has, let's say, a different efficiency of how much energy to release with supernovae or with supermassive black holes. So the whole idea here is that you have this very large parameter space, and you are sampling it, and you basically want to train models to somehow interpret this space. All right, let me talk about the GNL. It's probably the most interesting one. So imagine that every point here, every cell represents like a galaxy. What I will argue, I will have to convince you, is that probably the most natural representation of this is a graph. Even though in reality the data is really a point cloud, it's not a graph, because the connection between points is not clear. In principle, everything should connect with everything, because everything is interacting with everything through gravity. But we cannot really work with full connected terms. So usually, I give this talk to cosmologists and they need to say that you have a regular grid, you have a grid size, the grid is very, it's very fine, have a lot of zeros, you understand. So in all of this, basically the whole task about this, really to compute this post-linear probability is like we have now, from this simulation that I showed you before, we have thousands of virtual universes, the most, let's say, sophisticated universes ever created. Every universe has different values of the cosmological parameters. So the idea is basically that given a graph, you want to infer the positivity of the cosmological. So you want to do some kind of simulation like that from the graph. Let me just emphasize that for us, the galaxies, the only thing that they have is position, masses, and the modulus of the velocity. So which architecture we use? I mean, it's like a standard one, is like a DNN with the message passing, and it's a typical thing, right? We have the north features, the features, we have this layer, we apply several of them, and at the end of the day, apply the Boolean operation, and we work from vector, and from the vector, we can do less integration based. Maybe the one thing, again, I kind of cosmology, maybe these things are kind of obvious to you, but I think cosmology, but it's now is doing this kind of thing. So, anything that you have, I would be not that happy. So, for example, the Boolean operation was never clear to us if we should try the maximum, the minimum, all these kind of things. We tried to get different answers, so at the end, what we decided is to put everything together, so we don't use a single Boolean operation. We do all possible Boolean operations that we have. We concatenate the vector, then that was what we passed to the Okay, so this is like a lot of ones that we use. We do have used normalized flows here that we use something very simple. This is like a typical mean square error. It can be shown that when you do this, these represent the posterior mean, even without making an assumption about the posterior. You can have a quadratic there like this, where this is like a b parameter, and it can be shown that this represents the standard deviation of the posterior. So you have a very simple model. You have only like say two parameters per two values per parameter that represent the posterior mean. For us, it's enough. You can use normalized flows. For us, it's very important that the network is S3 invariant. And the reason for this is basically because imagine that is the galaxies from a particular universe. The value of the cosmological parameters is going to be the same. You will translate the graph. If you rotate the graph, it's going to be the same. So we're going to really compose the S3 invariant. So let me tell you how we do this, and I don't know if this is very precise.
So why the S3 and not just E3 that is sleeping the
Yes, in principle, we want to compose also the binding violation. Yeah. In the universe, usually we assume that we are symmetric to this, but there are some moments that are so different. But in this case, thank you for that. So, for every galaxy, remember we have positions and two scales, have the masses, and we have the modulus, the velocity. So the way that we construct the graph, this is like a feature of the graph, is like our graph is S3 invariant, basically just coming from the known features. That's really good. So for the known features, we just put like the masses and the velocities. And we don't use any position information from the nodes. So what do we know about the position information? So what we do is the following, is that imagine that we have the graph. So we can define some point. In our case, it's like the geometrical center, but it can be really any point of the graph. And then from this point, you can basically compute vectors like if you are interested in this edge feature, you will have this one vector, another vector, this vector. Basically, we follow that paper. And what we do is that we go as edge features, basically all possible information of a scalar quantities between all the spectrum. Right? So we compute basically one of them is like the distance between the 2 points, and the other things are basically like angles. And the beautiful thing about this is that this is already translational and rotational back. You can take this graph, you can rotate it. The angles are not going to change, the distance is not going to change. And you can both translate things and not change. So it's it's a very simple thing at the level of the known features, instead of writing positions that are not, let's say, S3 invariant, you basically write things in this language. Yeah. Then by construction, the model is S3 invariant. So this is how one of the typical graphs for us look like. Basically, we connect 2 points if the distance between them is smaller than even length. This length is a hyperparameter and we optimize for it. And this is basically what the model is. So somehow the model does not prefer a very connected graph. It would be like over expansion and all these things. But this is. So from the cosmological perspective, this is very nice because we only have like 1,000 galaxies. Very graph. By construction, the model is S3 invariant. Basically, what we always say in cosmology is that if you are doing this, you are extracting information from even the smallest scale. You can have two galaxies that are super close together. In principle, the graph is not extracting information from this. This is very different to what we do in cosmology. What we typically put a grid, and the grid is, let's say, very close. So then, basically, we train on, have like 1,000 of these graphs. We train at the end of this. And let me show you the results. So this is like a typical plot of true versus prediction. This is for one of these parameters. And every dot there with the other values, zero mean standard deviation. is coming from that. Of course, the closer that you are, the black line, the better. So this was for a model that we train on simulations. And we test on simulations that were run with the simple. So we know that this usually do well. The problem for us, and I'm pretty sure that this is another thing, is that if you train your model using some particular simulations, and now you change something of this simulation, let's say the code or something, nothing. So in this case, we were surprised. You test the model on different code, wars, another code, wars, another. So sometimes it was really robust. And on the cosmology, this is kind of remarkable. Right? This is like the very first time that in cosmology we are able to go to these incredibly small scales, dealing with all these nasty pieces that I showed you before about, all these energy release, supermassive black holes, and all these things. Basically, we marginalize these processes. So this is, it's kind of a completely new way of doing cosmology. Let me talk about the interpretability a little bit. So I don't mention this morning about using the kind of science maps interpretability. In our field, we do something very different. So imagine that you have your DNA, and you can write always instant features are going to be some function of L feature and top features. You can do a similar thing for the top features. At the end of the day, you can put everything together and it's going to do something. Imagine that you only have in one day. Basically, you can write the parameter, you are doing this expression as some functions that are like this. But the important thing is that these functions only then scalar functions. I mean, they could be vectors or anything, but if you are careful and you really design your DNA as a little more of the smallest, let's say, data vector possible, then the beautiful thing is that you can try to approximate these functions using symbolic regression, and get an analytic equation basically reproduce this. So this is a work that it was done by that student at Princeton. And basically, we took the GNI model that we trained before, and he was able to derive this set of equations that, in cosmology, you have never seen anything like this. But what is remarkable is that you take these equations, you apply it to a galaxy character, you get the correct result. It's still not clear to us what exactly this means, but this is some kind of like scope, right? It's like you combine DNNs, if you design them, you cannot use many layers. You can use like one layer, you can use the data vector as small as possible. But you might be able to derive frameworks that probably contain some physics already underlying the system. Let me talk before finish on this part. So we still have some challenges, but we are not like solved at all. We don't know how many big universe or even billions of galaxies that is really what we need to live in the real universe. This provides us really the most, I believe, the most important. I showed you before that the DNA that we have, you train on one simulation before, not them, but we were using positions, masses, and velocities. If you train your model only using positions, you train on one simulation, it doesn't work. And it's really unclear to us, I will be more than happy to tell you ideas about this. You can try to organize things, you can learn these kind of things, but it's really unclear to us how you can really generalize all these things. So that's a very big problem. Let me quickly just analyze this mention another maybe cool applications with GNLs that people are doing these days. So imagine that this is a dark matter area. So this is Bible before this very large concentration of dark matter. So usually, you can think of this like one galaxy, and around the Milky Way, there is some satellites galaxies. So again, you can represent this as a graph. And in astrophysics, for a very long time, we always wondered what is the mass of our galaxy? How heavy is the Milky Way? So people have tried many different techniques, of course. But if you have simulations, if you track the simulation, or if the simulation you don't track something that you can manualize over, then we can try to ask this kind of question. So in our case, we have a lot of simulations with a lot of system planning, so you can create graphs and basically train the graph to infer the mass of these kind of systems. And it works remarkably well. For instance, these are constraints on the mass of the big world. This is protected, so this is what we do with these kind of models. Here, it's only using like two subsets. If you were able to do more, you will get numbers. So for me, this is again, it's fascinating, you know, that you can measure somehow the mass of our galaxy with these kind of experiments without really making any assumptions in this. That's basically relying on simulations. And this is the very last thing. That's about the nature of that. So I told you the nature of that model is not a big problem in cosmology and in physics in general. What I'm going to show you is like two moves. So this is one move where we have like one type of dark matter. This is the standard one, dark matter is slow. This is another type of dark matter that is slow. It's just basically saying that dark matter might have some velocities. So what happens here is the distribution of dark matter of this dark scale, and these patterns are going to be basically focused in this region here. And this is like the glass, this is like the stellar. So what you can see is that this halo is kind of forming, accreting, mass, other halos. This is the galaxy in the center, you can see that the gas is accreting. This is going to produce a beautiful spiral at the end. And from time to time, if you look at here, you can see some explosions. This is an explosion maybe from supernovae, and this is like so what you can see the problem here is that already when you change the nature of that matter, things change a lot. The distribution of these satellites is really different in two cases, but also the morphology, the galaxies themselves. So, you know, these days where the community is wondering what can we do with the, let's say, machine learning, particularly GNNs, to answer this question. Because even in the field, traditionally, we have been looking at some particular property and some graphing properties, whether we just extrapolate information. So I think this is this is like one example of many galaxies in many different universes, different. And also trying to say that someone want to use this data set, everything's public, everything's it's like you know, super cool application. But yeah, this is like the last slide. Also, when you use CNN for this kind of things, for example, take a look at the distribution of satellites, the galaxies, using not only maybe the position, but you can also use maybe images itself, you can combine all these things in graph. Things work, and it's quite a lot. So, cosmology and astrophysics, these days we are really taking advantage of the work that you guys are doing. Conclusions, we live in a real universe. What about the laws of the constituents of the universe? That's really the most important thing for us. Historically, we have been doing this with pen paper, especially with numerical simulations. Now with deep learning, we are really seeing a revolution. You know, there are very hard questions that some of us, 5 years ago, thought that it would be completely impossible to solve. We are not solving that. And I think in astronomy, you know, many things, the number of representation of the data is grand. So that's why I believe GNNs, particularly, will have a I think my lab is somehow it was fully charged. So I'm going to stop here. Thank you very much.
Okay. Do you have a video?
I have a question. So before you evaluating, you said that GNN was actually very well, surprisingly well. You're evaluating the true like data, the parameter that you and the predicted.
We do some kind of coverage of these kind of things.
Yeah, then we look at this example, like how can you
Exactly. So we do basically like a coverage test because this is not like full posterior, is not really, let's say, like a coverage test. So there is a quantity like this kind of I square that basically is gonna be the equivalent to this coverage test. And we basically see that there.
It's sort of valuing how they estimate the true profit. And the
Yes.
profit here is like low damage. Right? It's the one like
The truth is low dimension.
like the data, like is it like just like how like what is data like? Is it like a
So in this case, it's only like a graph positions and masses. So then for this, you create a graph, and then you test the DNA. Okay.
You said that several problems that were thought impossible factors and go are being solved. What do you think should be the next one? Something that we hope to see soon. If you can explain it how there's something.
That's a good question. I mean, for that matter, the problem is that so for the whole you see that we have a model. The model is something that we trust a lot. So it's really a matter of inferring these parameters. So in that case, it's kind of clear. For that matter, the thing is that we don't even have a model. There are different proposals. So in that case, I think the volume parameter space is much larger, and it's not really that clear to me how you can take a model and you can infer the parameters. That case, you can see this is an anomaly. But to really say that this is like the best model, that's I'm not sure. So maybe things are gonna go in that direction.
So you mentioned at some point that you're concatenating all of these different cooling layers. So is there any specific reason that you're doing that for the cooling? And what is the difference between the idea that you have for the cooling with these principal neighborhood aggregation, the PNA technique for getting concatenating all of these, passing it to another layer of MLP and layering the.
Yes, so that's I mean, as far as I know, probably it will not really matter so much the volume that you do is as far as the network is sorted enough. But in our case, it's like because we didn't want to try it, the max, the mean, the sun is the best one. It's like let's put everything together, and it was not a problem for us. You think the memory perfectly. So it's like why not? Just you make it more general.
Any other questions?